Welcome to today's webinar, which is sponsored from ASHRAE Technical Committee 6.7, Solar and Other Renewable Energies. Today's presentation is on transforming building envelopes into power generators. But briefly, before I go into the presentation and our today's presenters, I'd like to give a short introduction into ASHRAE 6.7. So ASHRAE has 4 types of committees: technical committees, task groups, technical resource groups, and multidisciplinary task groups. And technical committees are the most common and address a wide range of topics. There are 3 types of memberships: voting, corresponding, and providential corresponding. And TCs are formed by a group of volunteers. So anyone who is interested in participating in the TC is welcome. The members are from diverse backgrounds and come from different facets of our industry. And the only thing that's really needed is an interest and willingness to help improve the work of the committee. So the basic structure of a technical committee is formed as shown in the graph. So by participating in a technical committee, you are immediately become a providential corresponding member. And then you can also take up some other roles within the committee, such as being part of a subcommittee or being like a webmaster who will be responsible for the web page of the TC and some other roles. The basic subcommittees that are in each TC include the handbook committee that writes and revises chapters of the ASHRAE handbooks that are consistent with the TC scope. The research subcommittee that is responsible for identifying needed research and developing proposals. The program subcommittee that suggests topic sessions or different courses and presentations in ASHRAE conferences. And the standards subcommittee that identifies needs for new standards or revises existing standards. So Technical Committee 6.7 is specifically focused on solar and other renewable energies. You can visit the website of Technical Committee 6.7 and see past minutes of previous meetings that the Technical Committee had. Also see past sponsored programs, such as the programs shown at the slide. For example, strategies for net zero energy buildings, which was presented at the last year's winter conference. And different research topic acceptance requests, such as a recent one that is on solar PV design guide. Technical Committee 6.7 has also launched a LinkedIn page where you can follow it and get notifications and for different events and upcoming meetings with the Technical Committee 6.7. And we also have a sponsored webinar series. This webinar is actually the 4th webinar that we are sponsoring, and the previous ones you can also go to our YouTube page and watch them on demand. So some key benefits of participating in technical committees is you can actually have an influence on industry standards and guidelines and give your perspective and your inputs into how you can better these, access to cutting edge research and knowledge, and of course engage with many professionals within the field of your interest worldwide, and exchange ideas and expand your network. It's very easy to participate in our technical committee. You just need to visit the ASHRAE.org and go to the communities page and select technical committees. And then you can very easily apply for membership at the technical committee of your choice. You can see the list of the technical committees as well on the ASHRAE website. You just fill the form. You don't even need to be an ASHRAE member to participate in technical committee. And you can also participate both remotely and in person into the technical committees. There's generally 2 technical committees per year during the winter and the annual society conferences, and they're in hybrid mode, so you can participate online if you cannot go in person. And it's open to the public. There's no cost, and you don't even need to register for the conference to participate in the technical committees. So we always welcome new members and are excited to see new faces in our technical committee meeting. The next one is actually in February, which is going to be during the Orlando conference in 8 to 12 of February. So going into our presentation today, so today we have two invited speakers, Véronique Delisle, who is a project manager in the Renewable Energy Integration Program at the CanmetENERGY Research Center of Natural Resources Canada. She manages projects related to building integrated photovoltaics, see potential and control of flexible loads, smart cities, and bulk power system modeling pathways for net zero regional and national grids. And Véronique also holds a master's and a PhD degree in mechanical engineering from University of Waterloo and Polytechnique Montreal, respectively. Erin Gaucher-Loksts is a research officer in the Renewable Energy Integration Program at the CanmetENERGY Research Center at Natural Resources Canada as well. She works on projects related to building integrated photovoltaics, photovoltaic potential in the built environment, as well as developing a platform for tracking smart grid and renewable energy standards. So today they will be presenting on transforming building envelopes into power generators. And without further ado, Véronique and Erin, the floor is yours. You can share your screen.
All right. All right. Can you confirm that you hear me and you see my screen, Ana Maria?
I can hear you. I can see your screen. Yes, everything is perfect. Yeah, it's on presentation mode. Yes.
Okay, excellent. Thank you. So thank you for the introduction, Ana Maria. So as mentioned, we will be, Erin and I today will be talking about transforming building envelopes into power generators. So more specifically, we'll talk about building integrated photovoltaics, such that at the end of this presentation, you should be able to differentiate building integrated photovoltaics, so BIPV, from other types of photovoltaic systems. You should be also able to describe the different categories and explain the challenges associated with this technology. So we will cover a little bit of context on why this technology is interesting and important. We will talk about the basics of BIPV, the types, the applications. We'll provide some examples of systems that are installed around the world. We'll also talk about the challenges, because it's not perfect necessarily, and the R&D activities that are being done internationally to address those challenges so that we can push the market uptake of BIPV. And I'll also provide an updates on standards and codes, which will be interesting because it's also related to some of the challenges with BIPV. Many countries have decarbonization goals. So decarbonization goals in all the sectors of the economy, buildings, transportation, and of course the electrical grid. Nearly 200 countries made the pledge at the COP28 to reach the Paris Agreement target of limiting global warming by 1.5 degrees C, and doing that by doubling energy efficiency, but also tripling renewables by 2030. So what does it mean to triple renewables by 2030? Means that the cumulative global installed renewable electricity generation, so solar, wind, but also hydro, bioenergy, geothermal, tidal, should reach actually 11.2 terawatts by 2030. Also means that PV and wind power should account for about 90% of renewable energy capacity additions. That PV and wind should grow at a rate of 16.4% per year, and that this represents investment in renewable power generation of $1,300 billion per year. So it's a lot of renewables. Is this possible? Well, if we look at the historical annual growth rate of renewables, and again, that's all renewable, not only solar, not only wind. If we continue with the annual growth rate of 10%, we will actually reach 7.5 terawatts by 2030. So that's below our target of 11.2 by 33%. If we take last year's growth rate of 14%, well, we will reach 9.7 terawatts by 2030. So this is still below our target by 13.5%. So solar is a subset of renewables. If we look at the bottom right graph, what we see here is the evolution of annual renewable energy installations. And what we see there is that in 2023, actually 75% of all renewable electricity capacity, okay, not energy, but capacity installation was PV, so photovoltaics. What countries have the most PV systems? So if we look on the bottom left, we see the theoretical PV penetration in 2023. So what is that? Is actually the theoretical amount of the percentage of the demand that PV production could provide. So it's energy here. So if we look at the European Union, where the 10% of the demand was theoretically met by PV in 2023. For the United States, it was 6%, and for Canada, 1.4%. If we look at the whole world, we're looking at 8% of the world electricity demand in 2023 that was supplied by PV, theoretically. What market are the biggest in terms of solar PV? So China was actually the biggest in 2023 with additional installation of 277 gigawatt. It actually represented 43% of the whole new installation in terms of capacity, again, in 2023. That was followed by European Union by 55 with 55.8 gigawatts and USA with 30 gigawatts. And in 2023, well, the cumulative global solar PV capacity was in the order of 1,624 gigawatt. So that's actually, and also 29 countries install at least 1 gigawatt in 2023. If we continue on looking at those global markets, so we saw it a little bit in the previous slide, but what's interesting here is that there are 3 countries that have almost 20% of their demand met by PV. So that's Spain, Netherlands, Chile. Then we have the group 14 to 17% with Greece, Australia, Israel, and Germany. And then 3 countries in the 12% range, Poland, Japan, and Belgium. So we're going to need more PV. There's no doubt about that. Where are those PV installations going to happen? So there's different types of PV installations. The one that you might be the most familiar with is ground-mounted PV systems that can be centralized. So centralized is when there is no consumption at the location of generation. So that's often utility scale PV systems. But you can also have ground-mounted systems that are distributed meaning that there is consumption at the place of production. So ground mounting is, of course, a large part of the current PV installations. But there are other types, agrivoltaics. So that's when you're combining PV production with agriculture. There are carports installation. There's infrastructure integrated PV. So that's when PV are used on roads, for example. And you will have floating PV as well. Floating PV is when PV modules are installed on a floating structure on reservoirs of hydro dams or water treatment plants. And then you have the building types of installations where you will find building applied systems. So that's when modules are added to the buildings, applied to the buildings. And then you're going to have integrated systems. So when the BIPV system is fulfilling some of the functions of the building envelope. But we'll go a bit deeper later on what this means. But for now, let's look at the potential on buildings, and more specifically, the potential of rooftops. So the potential that the rooftop of buildings have for hosting PV.
Yes, thank you, Véronique, for introducing the topic of rooftop PV. So one application, like Véronique mentioned, was to increase solar energy generation in the urban environment, which is having PV on buildings as either BIPV or BAPV systems. But how can we actually quantify this value? How much PV can actually be installed on our roofs? What is the actual number that we can calculate for different regions, for, in our case, Canada? So we have here 3 different terms that we used when quantifying the amount of PV that can be installed. So we have our first level, which is the technical potential. And that is the potential of, as if you wanted to put PV on every available surface on your rooftop, where PV can be installed, excluding places like roof chimneys or vents or anywhere it doesn't make sense to actually put a PV system. The second level is economic potential. So this is where you're taking the technical potential and then applying financial factors so that you can actually see what part of that potential is financially viable. The third and final level of the different terms that we have is the market potential. So this is, again, taking the financial aspect from the economic potential and then seeing what ultimately gets installed in market factors and at what rate. So maybe not now, but 20 years from now, maybe it makes sense to actually have a system installed. So we did a study to find what is the amount of PV that can be installed based on these 3 factors in Canada. And as you see here, these are the results that we found for the technical potential in Canada. And as you recall from the previous slide, the technical potential is the amount of PV that we can theoretically put on a roof. So this amount for Canada amounts to about 300 gigawatts of rooftop capacity. And to put this more into perspective, our current generation fleet in Canada is 154 gigawatts. So it's about double the amount of our current capacity fleet. For the annual electricity generation, we calculated about 247 terawatt hours for Canada, while our total consumption from all sectors in Canada is 546 terawatt hours. So that what this is the electrical potential amounts to about 45% of the annual electricity demand in Canada. Slide, please. Now that we have that technical potential, which provides the upper bound of what is possible to be installed, now here we have more the market potential, which is what is likely to be installed in the future and now as well. So the market potential includes financial considerations for the purpose of finding what is the forecasted installed capacity throughout the years. And here we have the distribution of the forecasted percentage of rooftop generation to the total electricity demand in 2050 for Canada for rooftop systems. And this was based on an analysis we did with 900 different scenarios with inputs of the PV cost, electricity cost, module specifications, maximum market share curves, which is based on payback, and also input parameters for our chosen model, which is the Bass diffusion model for market research and market evolution over time. So the result of that study is a range of annual electricity generation that is between 2 and 27% of the total electricity demand in Canada for 2050. So the annual rooftop BAPV and BIPV electricity generation potential amounts to about an average of 6% of the total electricity demand based on the market potential analysis in Canada. And this is very much down from the previous slide that we saw 45% with the technical potential. But although this number seems small now, but if you look at the numbers that Véronique mentioned a few slides ago, for the current solar energy generation from all applications, is 1.4% of the annual electricity generation in Canada. So if we increase only the rooftop application to be 6% of the demand in 26 years in 2050, that would be quite a big increase. So this was the analysis that we looked at for rooftop BIPV and BAPV and BIPV, but focusing more on the topic for this presentation, which is BIPV. Véronique will now go through what are BIPV systems.
Yeah, thank you, Erin. So clearly, rooftop has certain potential, but it's not going to be the only solution to supply all of our electricity, but yet it's there, it can host PV. So let's go in the main topic of the presentation today, which is building integrated photovoltaics. So I touched upon it a bit earlier, but what is BIPV? So it's when we have a component that not only converts solar energy into electricity, but also fulfills one or multiple functions of the building envelope. And what's a function of the building envelope? Well, it could be mechanical rigidity or structural integrity. It could be primary weather impact protection, shading, daylighting, thermal insulation, fire protection, noise protection. It could be separation between indoor and outdoor environments, like a semi-transparent PV window, security shelter or safety, like a guardrail, what we see as an example here. And how does BIPV compare to other types of installations? So if we compare with ground-mounted PV system, well, of course, what's interesting with BIPV, which is also true for BAPV, is that it does not require surface area beyond that of the building footprint, right? So the building already exists or is about to exist, and we're just using the existing surfaces. So that can be seen as interesting. The other thing is if we compare with BAPV, so building applied PV systems, and you will see example later, but it can definitely look nicer than building applied PV, so it can improve the aesthetics of the building. It's also two-in-one. BIPV, it's electricity production and building envelope function, so it can replace part of the costs associated with the building envelope. If I have PV cells in a window, well, I don't need a window in addition to that, right? It's two-in-one, so that's also a nice advantage. And if I compare with traditional building envelope components, well, of course, a regular window or regular asphalt shingle component does not produce clean and renewable electricity like BIPV will. Of course, you can consume some of the electricity that you're producing, so you can reduce your building electricity costs. It can increase the flexibility of the building with respect to the electric grid, and if it's coupled with batteries, for example, or any kind of storage, it can increase the resilience of the building. If we're looking at cell technologies that we can find in BIPV, well, it's more or less the same ones that we can find in standard PV modules. So among the most common technology that you will find is crystalline silicon. So you can have monocrystalline, polycrystalline, bifacial. And bifacial is when the two sides of the PV cells are absorbing solar energy and converting it into electricity. Crystalline silicon cells are rigid and opaque, although you can play with the spacing between the cells to achieve different level of transparency. Efficiencies of crystalline silicon modules will be up to 22%, and they will be impacted by temperature. So as the temperature increases, the efficiency will decrease at a rate of 0.5% per degree C. So it means if I have a 200 watt module at 25 degrees C, if this module is now at 50 degrees C, I will produce 175 watts. The lifespan of modules with crystalline silicon cells can be 25 years and more. Then you have thin film technologies. Thin film technologies that are Here, what we see, silicon base. So you can have amorphous silicon technology there. So the interesting thing with thin films is you can deposit it on rigid or flexible substrate. So that's giving some possibilities. And you can also play with the thickness of the layer of deposition. And with that thickness, you can achieve different level of transparency. So with the crystallines, you will space the cell to have transparency. In the case of thin film, you would just deposit less. Your thickness of your deposition will be less, and that will give you transparency. But of course, this will affect your efficiency. So modules of that type have efficiencies up to 9%, and they're typically a little less sensitive than crystalline silicon-based modules with minus 0.36% per degree C. But their lifespan is still about the same. And then you will have other thin film technologies like CIGS, cadmium telluride. And also you have other types of thin films that are more at the development stage, polymer base, perovskite base that we see at the cell level, but sometimes a bit less at the module level. So with those technologies, you can achieve flexible, transparent module, and also you can reach really different colors that you would be able to with other technologies. These ones more under development tend to be less stable, so their lifespan will be less, and they are also typically less sensitive to cell temperature. What you can do with glass, you can do with BIPV. And what we see here is a technique that is used to achieve different textures and different color. So this is a coating and printing method. So most coating and printing methods used in glass can be used in BIPV. For glass BIPV, any color, shape, and texture are possible. What we see here is a printing method. So different dots were printed at different degrees on the glass. And those dots were of different colors, so white, green, and black. And what this shows is that you can achieve really different colors just with this printing method. And of course, it affects also the temperature. So especially in the case of the black dots, we see on the right that the power loss is much more significant than with the other color. And of course, as the density of printing increase, well, the less light go through, and obviously the less efficient your module is. Which brings us, yeah. Go for it.
Sorry, I was on mute. So yeah, Véronique had mentioned different types of semi-transparent BIPV windows, but where else could you put BIPV? Where it can be placed? And since it is a building material and it's meant to replace different components of your building, so there's three main areas that you can be replaced by BIPV, and that is your roof, your facade, and externally integrated installations. So some examples of these would be using BIPV as your curtain wall, as your rain screen facade, your roof, a skylight, a balcony, solar shading, and other different applications. Next slide. So I mentioned that there are three different areas that you can place BIPV, your roof, facade, and externally integrated, but these could be further divided into 5 different categories. Category A and B are for roof applications, with category A that is inaccessible from the inside, and category B that is accessible from the inside, so you can touch the module from the inside. Category C and D are facade applications, where category C is inaccessible from the inside. So this could be a rain screen facade that is only outside of your building. And category D is accessible from the inside. So this can be a window that can be touched from inside. Category E is externally integrated systems that can be accessible or not from the inside. This would be solar shading, balconies, or similar applications. Thank you. To give an example of these categories, we have a few case studies to show, like we see here, for each different category. So in category A, for a rooftop installation that is not accessible from the inside, we have a headquarters in Switzerland with an installed capacity of 76 kilowatts. So this installation was a retrofit that was completed in 2021, which used a mix of active and inactive colored panels. And the coloring was custom made for this installation. Next slide. So this installation is an atrium for a building at the University of Alberta in Canada. It was completed in 2018 with an installed capacity of 10 kilowatts. This used custom-made semi-transparent panels with opaque cells distributed in a unique pattern over the atrium. So they had a different design, and they custom-made those panels so that they can have a unique design across the atrium with semi-transparent cells. Yes. So the next building is for the Red River College in Winnipeg, so in Canada. So they installed a BIPV facade on one of their buildings. It was constructed in 2021 with an installed capacity of 100 kilowatts. So this building used BIPV modules that were a bit more unique with spectrally selective coated colored solar glass instead of using pigments or dyes, so the color will not fade out with the passage of time or due to any sun exposure. Next slide, please. So this is a recent installation at the St. Mary's University in Halifax, Canada. This is a retrofit installation with an opaque facade as well as semi-transparent windows, and it was completed earlier this year in 2024. This is the tallest BIPV installation in Canada with 22 stories of BIPV. So this had a total installed capacity of 100 kilowatts. Next slide, please. So this installation is the Centre for Innovation, Technology and Entrepreneurship in Toronto, Canada, and is a bit unique compared to some of the other case studies that we've shown in this presentation so far, as opposed to the windows that we've seen in the previous slide for St. Mary's University or for the atrium windows, where opaque cells were distributed on clear glass to create that semi-transparent effect. For this case study, we can see that you can't really see the cells on those windows because this installation uses amorphous silicon semi-transparent windows so that the cells are also transparent. And they're very hard to spot from those pictures that we see to the right. So this installation was completed in 2018 with an installed capacity of 1.3 kilowatts. Next slide. And our final installation that we are going to show today is for the Ontario Association of Architects headquarters in Toronto, Canada. This installation is a BIPV canopy that provides shading to part of the building. This installation provides rooftop PV as well as a solar canopy to cover the entire surface of the roof on the building. So the canopy is the middle section of the roof, placed atop an opening in the U-shaped building to provide shading to that part of the building. This installation was completed in 2020 as a retrofit installation with a capacity of 26 kilowatts. So the BIPV portion of that installation generates around 40,000 kilowatt hours per year. So these are some of the case studies found in Canada and other parts of the world. Now I'll hand it back to Véronique, who'll go through some of the challenges that can be seen in the BIPV market when trying to install one of these systems.
Yes, because all the case studies that we just looked at had to go through some challenges to make it to a final building. So yes, there are still challenges remaining with BIPV market uptake, and these challenges can be categorized into 3 parts: so cost benefit, technology and performance, and regulations and know-how. So let's start with cost benefit. The cost of products can be a challenge, and the difficulty here is comparing with the alternative. So when you're looking at the cost of a BIPV system, again, you have to think that it's 2 in 1. So you have to, when you're looking at the cost benefit, you have to do the right comparison with the alternative. So that's one thing. Financial incentives can be often challenging for BIPV because BIPV might not be included in any kind of incentive or subsidies, or they might not be BIPV specific. So sometimes it's kind of in a gray zone, which makes it difficult. Depending on the country, some countries are, of course, more advanced than others with BIPV, but in countries where it's still a bit more of a niche technology, it can be difficult to estimate the cost of projects because the cost of installation is challenging because there's not a ton of projects that you can compare with and base your costs on. And the availability of products also makes it challenging to know, okay, how much is going to cost me to buy over there, to ship to my country. So it can be difficult to estimate the cost of projects. And the long-term value also is not always easy to define because of all the reasons mentioned above. In terms of technology and performance, again, it depends on the country. And in Europe, there are several products, but in other countries like Canada, for example, the amount of products available can be limited. So that's a challenge. Lack of standardized integrated options. Also, because it's a building component, often it's customized. It has to be customized, which adds to costs as an instance. Lack of performance data. Also availability of qualified personnel, often linked to the locations where there hasn't been a ton of projects. So your electrician maybe is not super familiar with the technology, or your regular building envelope people are also not super familiar, so that can be difficult. And then there's regulations and know-how. There are some standards and codes. We will talk about it later, but there are still challenges remaining. Also, well, the same as for buildings, right? When you're designing and constructing a building, you have your national regulations, you have your regional, and then you're gonna have your sometimes municipal regulations. So you have all those requirements that you have to deal with. But when it comes to BIPV, well, it's 2 in 1. So it comes with twice the requirements, the electrical, but also the building part. So it can be a lot of requirements, and navigating through all those can be difficult. And also the limited design guidelines, although we will mention later that this is being addressed. So all these challenges, not all of them, but a lot of them are being addressed under the International Energy Agency, so IEA, Photovoltaic Power System Program. So that's one of the technology collaboration program of the IEA, PVPS. There is a task called Task 15, which is enabling framework for the development of BIPV. And this specific task has been going on for many years now, such that it's currently in its 3rd phase. Third phase that's going to be run until the end of 2027. It's collaboration between 17 countries, and these 17 countries are dedicating BIPV experts to work together to create an enabling framework to accelerate the penetration and deployment of BIPV products in the global market of renewable energies and in the construction sector. So again, the dual challenge of BIPV, the fact that it's electricity, but it's also construction. So in the next slide, I'll be talking about what this group is actually tackling to remove some of these challenges that I just mentioned. So task 15 has 5 different subtasks. Subtask A is looking at challenges and opportunity of BIPV in a decarbonized and circular economy. So often building regulations of the net zero kind, of energy efficiency kind, are not necessarily inclusive of BIPV. They talk about PV, they talk about energy efficient building materials, but they don't necessarily talk about BIPV. So what would that mean to include BIPV in such types of regulations? There's also a second aspect looked at in this subtask, which is the BIPV potential and market. So Erin touched upon the study that was done in Canada for the BIPV technical and market potential. That was just on rooftops, because as we saw, BIPV can be on facades, BIPV can be externally integrated. You can have guardrails, you can have canopies. So what's actually the potential, the technical potential, the market potential of BIPV, and what's the actual market too? How much is installed right now? That's sometimes very difficult to know. IEA task members have to report on the amount of PV installations that they have in their respective countries, how much is centralized, how much is distributed. But it's hard to go more in details when it comes to, okay, how much is roof, how much is facade, how much is building integrated. It's the kind of numbers that are very difficult to obtain. So that's what this subtask will try to address. Subtask B is about BIPV characterization and performance, pre-normative international research. So IEA is not a standardization body, right? They do R&D, and they do R&D that after that can be used to feed into standards and codes. And what's great about it is it's often not the exact same people, but some of the same people, or it's all a community that knows each other. So it's really helpful to do the research in IEA and then try to inform standards committees with those results. Some of the aspects that are being tackled is the characterization of shading on BIPV facades, outdoor testing of BIPV solar heat gain coefficient. So it's one thing to calculate the solar heat gain coefficient of windows, that's known, indoor and outdoor, but when it comes to BIPV, it's different. You're producing electricity. There's a different way you need to do that. And what if you have color BIPV even? So it complicates a little bit the calculations. And guidelines for performance modeling of colored BIPV, right? Because all the models for PV out there were not necessarily developed or validated against colored PV or colored BIPV systems. So are the models currently existing appropriate for colored BIPV? BIPV in the digital environment, that would be subtask C, so representing BIPV projects in open building information model format. Subtask D is about BIPV projects and demos, innovation and long-term behavior. So how do we monitor BIPV systems in terms of key performance indicators? How do we know if they're working as expected? And also we're looking at the long time stability and durability of colored BIPV. So a lot of the BIPV systems out there are not necessarily old yet, but we have data for systems of 5, 10 years, 15 years. How's the system performing over time? And finally, the last subtask is about training, dissemination, stakeholder collaboration. So the research that is done in the IE, it's always, the goal is to make it useful, right? So you want to make sure that you are addressing some of the needs of the industry in the research that you do. Some of the publications that was done by this specific group, so by Task 15, because again, we're in the third phase, so it's been going on for many years now. So a guide for technological innovation system has been created. The categorization of BIPV application was also done by this group, some of the content that I've shown earlier. Development of business cases. So how did the business case for the different project was done? How did they came up to the conclusion that it made sense to do BIPV? So that's one of the reports. BIPV design performance modeling and analysis of requirements, specifications, regulation of BIPV. So if you're doing a BIPV system, what are the requirements that should be met in terms of the electrical part, but also the construction aspect of it? And remember, before I mentioned one of the challenges was the lack of design guidelines for BIPV. And one of the great products of that working group is actually a technical guideline that is available and that actually will be discussed in the next webinar of TC6.7. And this guideline, it contains information on what to consider when you're designing a BIPV system with respect to energy production, thermal performance and solar gains, daylighting, water management and weatherproofing, acoustic performance, safety and reliability, environmental impact, aesthetics and architecture. And you can see there a number of projects that are all around the world that were used to develop the content for that guideline. So let me touch now on standards and codes when it comes to BIPV and explain why it's such a challenge. So on this picture, what we have is a facade with that's divided in three parts, right? So the upper part is a BIPV window. In the middle, we have a BIPV solar protection system. And at the bottom, we have a BIPV facade that is opaque. So all parts, they, of course, produce electricity, right? That's a given. They also impact the heating, ventilation, and air conditioning load. They impact the occupant for comfort, obviously, because they have an impact either on lighting or the temperature inside the building. If we're looking at the BIPV window and the BIPV facade, well, they also impact the hygrothermal performance of the building. And if we consider the BIPV window and the BIPV solar protection system, well, they have an impact on the amount of daylighting that will come in. So consequently, the amount of electricity consumption that's going to be dedicated to artificial lighting. So it becomes very evident with this that BIPV system impact the buildings. And of course, they serve one or multiple functions of the building envelope, so it has an impact on the building. So when it comes to BIPV, it must comply with codes and standards for both the PV, but also the buildings. So where are we on standards? So I'll just tell you a bit the story here is that one of the first, if not the first standard on BIPV where it came from the European group, so EN. So there was that was in 2016. So it was a two-part standard, part one on BIPV modules, part two on BIPV systems. So explaining basically the different requirements. That inspired the IEC, so International Electrotechnical Commission, to develop an international standard on BIPV. That was also -1 for module, -2 for systems. So that was in 2020. Recently in Canada, we adopted actually with deviations, the IEC 63392 standard. So that became, with deviation again, the CSA standard, so a Canadian version of the standard. And so that's a little bit the story. And right now they are revising the EN standards. You can imagine that this will eventually influence the IEC revision and of course the Canadian revision. In parallel, there is a IEC and ISO joint working group on BIPV. So that's the joint working group 11. And this working group assumes responsibility for ISO TS 18178, so glass in building, laminated solar PV glass for use in buildings, and the IEC 63092 series, which touches on PV. So this joint working group, they are put together so they can develop specific aspect of BIPV standards that touch, again, considering the electricity part, but the building part, and in this case specifically when it's used, when it has glass, right? Because it's the ISO TS 18178, which is glass in building. So since they're all inspired from one another, I'll focus on the IEC, the international one. So what does it contain? It contains electrotechnical requirements, as well as building-related requirements, and those requirements vary according to the presence of glass panes. So there are aspects related to mechanical resistance and durability, safety in case of fire, hygiene, health and environment, safety and accessibility in use, protection against noise, energy economy and heat retention, as well as sustainable use of natural resources. And in those standards, a lot, when it comes to the building-related requirements, there's a lot of, well, for your building-related requirements, read your national, regional, and local building code requirements, right? So it helps, but it's still like, okay, I still have to look at everything that is related on the building side. And the other challenge is that those specific building requirements were not necessarily developed for building components that were going to produce electricity, right? So if you're just looking at the safety in case of fire and you point to your building code and your building code says, okay, well, if you have a roof, it has to do this, this, and this. Well, these specifications, these requirements were not necessarily developed by the building code developers having in mind a product that was going to produce electricity. So this is worldwide, pretty much a lot of countries identifying that as an issue, because there is a whole need to review also the building related requirements that we're pointing out to, because these were not necessarily developed for that. And also because they are treated separately, the electrotechnical and the building related, there can definitely be some duplication at some point, right? Because PV modules have some tests for mechanical resistance and durability. Building related requirements also have those requirements. So if I have to meet both, then I have to do similar tests, maybe twice with slightly different loads. So, or I do the worst of the two. So even though those standards are helping in terms of requirements, there's still a lot to do in standards and codes to limit or to reevaluate what are the actual requirements of BIPV and maybe streamline this a little bit, because it can be a lot to deal with. But it's possible. There's tons of buildings that we've seen, so it's still possible. So this was for the standards, the updates on challenges and standards and codes. So as a conclusion, I think it is clear that there's going to be more PV. PV is needed. It's not the only solution, of course. With electrification, we're going to need a lot of new electricity generation that's going to have to be clean and hopefully renewable. According to the IEA, there's 100 million of households that will be relying on rooftop solar PV by 2030. So that's quite a bit. And 190 gigawatts of PV on average should be installed each year. So the future will have more PV systems. Buildings have available surfaces to accommodate solar production. It won't be enough for all the solar we need to install, but it certainly is one way to have solar production. And unlike PV systems added to buildings, well, BIPV can integrate more aesthetically and also replace part of the cost associated with the building envelope because it's really 2-in-1. So on that note, Anna Maria mentioned it already, but since this was presented by TC6.7, I want to encourage you, if you're interested in becoming a provisional corresponding member, if it's not already the case. That's how it starts. And to do that, you just need to push that button here, join TC6.7. You're already going to be a provisional corresponding member for 2 years. And then after 2 years, you can get more involved depending on your interests. So on that note, Erin and I will be happy to take a few questions.
Thank you very much, Véronique and Erin, for the very interesting presentation. So I'll go through the questions that I see in the chat. Firstly, Janice Means is asking, how does the color coding affect the efficiency of the PV panels? You touched a little bit on it, but you can maybe elaborate a little bit.
I can answer that a bit. So the coloring on the panels does affect the efficiency, and more so with different coloring that you have on the panels. So say you have a white coloring for your panel, it means that the electricity will be reduced by quite a bit more than say you have a black coating on your panels. To say how much it decreases by would probably depend on what kind of module you have in the first place and the method you print or apply that color coding. But yeah, it will decrease. So like say you had 25%, maybe with a white coating, you might go down to 10%. This is just some numbers to get you a sense of how much it could decrease the efficiency. If you have anything to add to that, then Véronique, you can go ahead.
Okay. Nice. And for the cost of the colored, I guess it's more expensive, I assume. So what do you think the motivation of colored PV would, I guess, be only on the architectural like enhancement usually? What is usually the motivation? I don't know if you're familiar.
A bit, I would say. It would be more on the architectural side. So if you want your building to look nice, you have different color codings. You don't want to showcase the PV cells on your building, then you can have coloring on it. If you want a nice pattern, as well as I know for some of the European countries, they have specific regulations on the color of certain aspects of their building, especially historical buildings. So having colored PV would help in that aspect as well.
So it would essentially be, in those cases, the only option to integrate PVs, to use colored PVs.
Yeah, exactly.
Okay. So Costas Balaris is asking, can you provide some information on the cost of the different installations and PV types?
Yeah, cost is I mean, you know what? Cost can be the exact same cost as a regular PV module, right? Because we didn't show examples like that, but sometimes your external building envelope material can be regular PV module with a regular PV mounting system. So it can be the same price as a regular PV module. And then it can vary a lot depending on customization, what you're doing. And of course, if for a project you have, and we saw some of those projects, different modules of different size with different number of cells that can add to the cost, but it's always what is the alternative, right? What was I going to do? I was going to put architectural glass that is not cheap in the first place, and I'm adding solar cells that are pretty cheap in it, but yes, the overall might be more than my regular architectural glass, but I'm producing electricity, right? So you have to do the whole cost-benefit analysis because the upfront costs might be misleading. And it could be as much as your regular PV, as little as your regular PV module too, depending on some applications.
Yeah, okay. Okay, Janice Means is asking if you can send her an email with some information on amorphous silicon transparent PVs. Yeah, so that's just a note, I guess. And
sure, but please note also that when you're going for thin film and transparency, especially amorphous silicon, it's a different level in terms of efficiency. The example that Erin showed with the Seneca College, that's 2.7, like if you calculate the watt and you look at the area, it's actually 2.7% efficient, right? So it's not, but the cost came with it, but is it enough to compensate? So it's again the cost benefit analysis, and also there are elements that have no price, right? Aesthetics is hard to price. So if it's very high in terms of your the items in your decision-making process, maybe it has value, maybe it doesn't, but yeah.
Yeah, she's also has on the same comment, Stanford Ovchinsky first proposed that amorphous silicon could transmit electrical signals just as crystalline silicon does. I don't know if you have a comment.
Signals?
To
look at the question.
Yeah. It says Stanford Ovchinsky first proposed that amorphous silicon could transmit electrical signals just as crystalline silicon does. I'm not familiar with.
I'm not familiar with that either, so I don't
sorry,
have much
Janice.
to comment.
Yeah. Okay. Costas Bar is asking, will it be necessary to also be thinking of batteries and storage?
It depends of your size. I mean, at this point, it doesn't become a BIPV specific thing, right? It's depends what you're looking for. Depends on the size of your system. Maybe your system is relatively small compared to your overall building energy consumption, such that it doesn't make much sense. Or maybe you are looking for resilience, and that has a lot of value for you. So it's it's different price if you're going down the battery option. But at this point, it's not necessarily a BIPV specific thing. It's a PV on building discussion.
Yep. And Peter Luke is asking, is there any incentive from Canadian government currently?
Well, so there is it's not BIPV specific. It's PV in general, well, renewables in general. So you can look at the investment tax credit, and you can also and you can also look at the greening government program, I believe, maybe to take with a grain of salt, but it might apply to that. But for sure, there's nothing BIPV specific that I'm 100% sure of. And then becomes, okay, let's look at the PV aspect, and does it fit or not? And then provincial wise, you can also find by province your and even municipal wise, sometimes you'll have incentives. So that's yeah. But federal government, those would be the two with a little asterisk, like to check if BIPV really fits into that.
Great, thanks. I have another last question. I was wondering about the environmental impact of different technologies like embodied energy. Is this part of goals that Canada or internationally are they counting these and like the recyclability as well of the PVs that is starting to gain a lot of attention as we're like reaching the end of life of a lot of PV installations. Are you familiar?
Yeah, so it is being looked at in, I don't think in TAS 15 they had a lot of success. There's very little people who are interested in it, but there's other tasks within PVPS who are looking into it.
Well, just to insert a little bit that they're trying to have one on environmental labeling in TAS 15. So it seems like it is going to be coming up, but sorry to interject into your comment, Véronique. I'll leave it to you to finish what you were talking about.
Yeah, no, that's fine. And the other thing is, yeah, when you're looking at embodied energy, you also have to compare with the alternative, right? So we will need more electricity. There's no doubt about that. Cleaner or not, there's going to be more demand. So what's the alternative? You have PV, you have wind, you have hydro dams. Like you have to compare with the alternative. So yes, it's not zero emission embodied energy, but what are the embodied energy of the alternatives? So I think we shouldn't forget that.
Thanks. Thank you for the answer. M. Mata is commenting a very interesting aspect to integrate into building components, but we build buildings to last a long time. What happens when the component no longer generates power or the technology changes? Can you address the problem of replacing a part of the building? If that happens, it would seem an undesirable cost in the life cycle cost of the building.
Yeah, for sure. I mean, Erin, did you want to go?
Well, you can.
Okay, well, I'll start and you can say if you want to. I mean, some of the examples that we show were retrofits, so it is possible, you know, when you're about to change your windows, or might as well put BIPV. But that, I guess, the question here is more, you went for BIPV, but then you need to replace part of it. It depends on what it is, but usually they make it plug and play enough such that it's okay. One of my, I don't know, for XYZ reason, my window got broken. I have to replace my window. Well, I have to replace my BIPV window. It's more or less the same, right? If you thought of the electrical connections properly, such that it's relatively plug and play. And I know for roofs, they also think of that, like when you need to go back and replace some parts of it. So at that point, it becomes a design aspect when you think of your racking and your electrical connections to make sure that if something is problematic in the future, it's doable to change part of it without changing the whole thing.
And just to add, in the design guidelines that are coming up soon or are currently published, they mention a specification for BIPV applications to have a life of over 30 years, I believe it is. So in that aspect, if your system is still generating power and it still acts as a building material, even if it's not generating power, if it's still intact, it can still be used as a building material and should last for over 30 years. So,
that's true. Good point.
Do you think that we will be seeing more BIPV in Canada? What is your opinion?
I see definitely more interest. That's for sure. I see more interest. I always get the same questions: who sells them? Where can I find them? And it's a bit of a chicken and egg, right? Not many systems, so not many business to sell or distribute products. And actually, a lot of the systems that we see are institutional to a certain extent. So a school, a government building, so do I think I do not have a crystal ball, but what I know is that I hear more interest, and And the more, I think the more system you have, the more, oh, it's possible, it's doable. Oh, they've done it. Oh, they've had it for 5 years. They've had it for 10 years. It might work. So it's I think it's building that knowledge that it's not that, you know, they have it a lot in Europe. It's possible. It works. If it's done well, it's going to be as good as your regular building envelope, and it's going to produce electricity. So why not? So we need to build that, I can think, minimum number of projects so that the confidence in the technology is built. But yeah, I don't know, but I hear more interest.
Nice. Okay. Thank you very much. I think we can conclude. I don't see any other questions. Yeah, so let me check the Q&A. No. Okay, so I'd like to thank you both for giving this presentation and showing us, giving us a good, like, from starting from the beginning about what is the PV potential, the BIPV concept, everything. I think it was a really good presentation, especially for someone that doesn't know. So it gave a really broad understanding of the technology. And thank you everyone for participating in the webinar. And we hope to see you at the next one as well. Yeah.
Great. Thank you, Anna.
Yeah. Thanks, everyone. Bye-bye.